I'd like to thank you all for inviting me here. For the next hour or so, I'd like to tell you how to measure everything you've always wanted to know about an ultra-short laser pulse. Let's begin by noticing the interesting fact that the vast majority of humankind's greatest scientific discoveries have resulted directly from more powerful techniques for measuring light. Microscopes led to the field of biology. Telescopes have given us the field of astronomy. X-ray crystallography solved the DNA structure problem. Spectrometers provided the atomic emission spectra that inspired and then confirmed quantum mechanics. And the Michelson interferometer provided a dark cloud over classical physics that eventually led to special relativity. A wide range of modern technologies, from today's numerous powerful medical imaging modalities to GPS, have resulted from more powerful light measurement techniques. Behind everything I'll tell you lies a dilemma. Most light is broadband, and hence by the Fourier transform, ultrafast, with temporal details as short as the shortest events ever created. But in order to measure an event or its details in time, you need a shorter event. For example, to study this event, you need a strobe light pulse that's shorter. But then to measure the strobe light pulse, you need a detector whose response time is even shorter, and so on. So now, how do you measure the shortest event? The shortest events ever created are ultra-short laser pulses, and it's now routine to generate pulses femtoseconds long. So how do you measure such a pulse? Well, by definition, the shortest event available is the pulse itself. But that isn't good enough. It's only as short as the pulse. It's not shorter. First, what is it that we're trying to measure? A light pulse has intensity and phase versus time, and also space, but we'll consider space later. Its electric field versus time can be written in terms of its intensity, I of t, and its phase, phi of t. Alternatively, in the frequency domain, it can be written in terms of its spectrum, S of omega, and spectral phase, phi of omega, where we use a script phi symbol because the spectral phase is different from the temporal phase. We need to measure the temporal or the spectral intensity and phase. Knowing only the intensity is called the one-dimensional phase retrieval problem for obvious reasons. It's quite infamous because it's badly ill-posed, which means that there are infinitely many possible spectral phases if we know only the spectrum, even if we have additional information such as that the pulse is very short. By the way, mathematically, 1D phase retrieval is ill-posed due to the fundamental theorem of algebra, which says that you can always factor polynomials. Interesting. Keep this in mind, as we'll be talking about it more later. Now let's talk about the phase. The phase, whether temporal or spectral, determines the pulse's frequency or color versus time. A measure of the color at a given time is the instantaneous frequency, which is given by the center frequency minus the time derivative of the temporal phase. The simplest non-trivial temporal or spectral phase distortion is quadratic, which corresponds to a linearly changing instantaneous frequency versus time. This effect is called chirp, in analogy with the sound that birds make. This means a pulse electric field like the one shown here at the lower right, called a linearly chirped Gaussian pulse, but it also has a Gaussian temporal intensity. This is actually the most commonly occurring pulse in ultrafast optics. It results when a pulse passes through a medium with dispersion, and all media have dispersion. So we'd like to be able to measure it, but also potentially much more complex pulses in addition. What can we reasonably demand of a pulse measurement technique? Well, obviously the intensity and the phase would be nice, but most techniques average over many, potentially quite different pulses. Unfortunately, when a measurement averages over many different events, it faces an impossible task. The measurement can only provide one result, and no single result can be correct. It's impossible for the measurement to accurately represent the events. So given that the task might be impossible, what should we expect? Well, first, because pulse shape stability meters don't exist, this task falls to our device, which therefore needs to provide a clear indication as to whether pulse shape instability is present in the pulse train. And even if there is instability, the measurement should provide some characteristics of a typical pulse, such as the correct pulse length. Ideally, the measurement would also yield a typical intensity and phase, and it should be able to do this for even a complicated pulse. Otherwise, it'll mistake complicated pulses for simple ones, which would be bad. And we'd like the device itself to be simple, because you shouldn't need a PhD in pulse measurement to measure a pulse. Oh, and single-shot operation would be nice, so we don't have to worry about this whole instability thing in the first place. Yes, this is a lot of demands, and most techniques fall quite short. But we'll find that we can actually do all of this, and that's what I'm here to tell you about today. Let's begin in the 1960s, when it was realized that the shortest event available was the event itself. So researchers knew that they'd have to use the event to measure itself. Splitting the pulse into two replicas, crossing them in a nonlinear optical crystal, varying the delay tau between them, and measuring the nonlinear optical signal pulse energy versus delay yields the intensity autocorrelation. Here's a more detailed diagram of its setup. The signal field, E sig of t and tau, is proportional to E of t minus tau. So the signal intensity is proportional to I of t minus tau. And because detectors are slow, the intensity autocorrelation is then given by the integral of the product of the pulse and the delayed replica of itself. Here are three pulses of varying complexities and their autocorrelations. Notice that as the pulse becomes more complex, its autocorrelation approaches a broad background plus a narrow spike atop it, called the coherent artifact. So as the pulse becomes more complex, the autocorrelation actually becomes simpler. As a result, it's easy to see that retrieving the intensity from the autocorrelation is fundamentally impossible. Simply put, information is lost. It turns out that retrieving the intensity from its autocorrelation is also mathematically equivalent to the one-dimensional phase retrieval problem, so the intensity can't be obtained from the autocorrelation. This problem is also highly ill-posed. Now, clearly, if every complex pulse has such an autocorrelation, averaging over an unstable train of complex pulses will yield the same autocorrelation. In the 1960s, this wasn't immediately known, and some researchers confused the coherent artifact for their pulse, and so reported much shorter pulses than they actually had. Shorter pulses are more exciting, so wishful thinking probably had something to do with it. Fortunately, Fisher and Fleck explained the effect in 1969. So you might think that that'd be the end of such misconceptions. But you'd be wrong. To see why, here's a stable train of 12 femtosecond long simple pulses, which yields an appropriately simple autocorrelation. No problem, autocorrelation does fine. Now we'll add to the stable component a longer unstable one. You can see the beginning of a coherent artifact in the autocorrelation. But now consider a train of only somewhat complex unstable pulses. Despite the instability, this train yields a fairly simple autocorrelation, easily confused for that of a simple, stable pulse train. A curve fit yields a pulse length of 16.7 femtoseconds, badly underestimating the actual pulse length, the actual instability, and the actual complexity. So it's easy to make this mistake, and people still do. The coherent artifact is actually even more of a problem than you might think. Most modern interferometric techniques, for example, measure only the coherent artifact. Here's a pulse and its trace using the spider technique, which retrieves the intensity and phase of simple stable pulses quite well. Now if we add a random component, generating an unstable pulse train, what does spider measure? In this case, spider yields only the shorter, non-random component of the pulse train, the coherent artifact. The random components of the pulses generate intensity fringes with random phases, and so cancel out of the spider trace, leaving only the spider trace of the stable component. Interestingly, spider accurately measures the average spectral phase, but that's the definition of the coherent artifact in the frequency domain. Spider and other modern interferometric techniques cannot distinguish between a stable train of short simple pulses and an unstable train of long complex pulses. As a result, they should never be used to measure pulse length. Another interesting case is double pulsing with random separation or random phase between the pulses. Most lasers double pulse randomly when pumped too hard. Here we see the spider trace of a train of double pulses with random relative phases. Notice that the trace is identical to that of a single pulse. And here are the spider retrieved intensity and phase versus time and frequency. Spider retrieves only a single pulse with no hint of the other pulse, and spider retrieves a flat spectral phase along with the single pulse. Again, only the coherent artifact, not the actual pulse. In general, interferometric methods measure only the coherent artifact and fail to see double pulsing unless it's very stable. So pulse measurement isn't as easy as people first thought. You can easily mess up, so it's important to be very careful. Indeed, spider was used for many measurements over 15 years before this was realized. And it's not that all spider pulse length, complexity, and stability measurements have been wrong. Some certainly have been, but the rest are simply unconvincing, yielding only a lower bound on the pulse length, complexity, and stability, just as autocorrelation does. So we shouldn't use interferometric approaches to measure pulses. It's better to measure spectrograms, the spectrum of the product of E of t and a variable delay gate function g of t minus tau. G of t minus tau gates out a piece of E of t centered at tau, and we then measure the spectrum of this piece versus delay. The spectrogram yields the color and intensity of E of t at the time tau. And here are spectrograms of linearly chirped Gaussian pulses, where you can see that the slope of the spectrogram reflects that of the pulse frequency versus time, and the intensity versus delay of the spectrogram tells us the pulse intensity versus time. Like a musical score, the spectrogram visually displays the frequency versus time and the intensity as well. So how do we make spectrograms? Well, the approach is called frequency-resolved optical gating, or FROG, and it's simply a spectrally resolved autocorrelation. The autocorrelator's energy detector is replaced with a spectrometer, and the result is a spectrogram. You can use any fast nonlinear optical process. Unlike most spectrograms, however, here the pulse gates itself. It has to. There's no shorter event available. The pulse isn't shorter than the pulse, so doesn't a spectrogram lack sufficient temporal resolution to measure the pulse? Well, imagine that the gate is infinitely short. Then it would gate out an infinitely short chunk of the pulse, which would have an infinitely broad spectrum and hence contain no frequency information, which would be bad. So in spectrograms, it turns out that the gate need not be, and actually should not be, much shorter than E of t. As a result, the spectrogram resolves the dilemma. It doesn't need the shorter pulse. In practice, it temporally resolves the slow components and spectrally resolves the fast ones. Here's a very complex pulse and its frog trace. The first point to make is that there's no coherent artifact. Also, the frog trace is appropriately complex, so information about the pulse isn't lost as in autocorrelation. It turns out that for spectrograms, pulse retrieval is equivalent to the two-dimensional phase retrieval problem, which, unlike the 1D phase retrieval problem, happens to be a very well-behaved problem that can be solved easily. Now recall that phase retrieval and the fundamental theorem of algebra are actually related. Well, 2D phase retrieval works because the fundamental theorem of algebra actually fails for polynomials of two variables. So how is the pulse retrieved from its frog trace? Well, the best algorithms are based on the generalized projections algorithm. A projection maps the current guess for the waveform to the closest point in the constraint set. The green oval is the set of E sig of t and tau that satisfy the nonlinear optical constraint that E sig of t and tau is proportional to E of t minus tau. The brown oval is the set of E sig of t and tau whose bag-squared Fourier transform is the measured trace. Both must be satisfied to yield the correct signal field, which yields the correct pulse. Note that in this picture, for any initial guess, the algorithm finds its way to the correct solution. Convergence is actually only guaranteed for convex sets, but it usually occurs even with non-convex sets, and in particular in FROG, but not always. So we recently developed a 100% reliable FROG algorithm called the Rana approach, which stands for Retrieved Amplitude N-Grid Algorithm. It turns out that we can retrieve the pulse spectrum directly from the frog trace, and we use smaller data arrays for the first sets of iterations, as well as several initial guesses. Whereas the usual generalized projections approach only converges 1/2 to 3/4 of the time, see the middle columns, Rana, on the right, achieves 100% convergence in all cases, and it works for noisy traces and even for very complex pulses, the time bandwidth products of which are about 100, which means that 100 spikes in the intensity or spectrum can occur, and the Rana approach still works. The Rana approach not only always converges, but for complex pulses, it's actually quite a bit faster. Okay, so how well does FROG work in practice? Well, here's a measurement of the 4.5 femtosecond pulse. Notice the excellent agreement between the experimental trace and the trace computed from the retrieved pulse, which provides a nice check on the measurement. This is because the FROG trace massively overdetermines the pulse. There are n² points in the trace, which corresponds to n intensity points and n phase points, or just 2n points. So most things that can go wrong reveal themselves in discrepancies between the measured and retrieved traces. And indeed, this overdetermination is critical for determining instability. For unstable trains, Frog has what we call a multi-shot coherent artifact, just as autocorrelation does. But because Frog's algorithm must fit one pulse to n squared points, it can't fit to it and smartly ignores it. So as expected, Frog retrieves the pulse from the stable pulse train in the top row perfectly. For the random pulse trains, Frog retrieves the correct pulse lengths. But equally importantly, disagreement between the measured and retrieved Frog traces reveals the instability. Other versions of Frog do even better. Here we see their performance for unstable pulse trains. One version uses a third-order nonlinear optical process called polarization gating, which we call PG-Frog, and another uses a known reference pulse to gate the unknown pulse to be measured. This latter version is just a spectrogram, but people often call it X-Frog or cross-Frog because it's a spectrally resolved cross-correlation. These Frog versions also reveal the instability, and even better, they also yield the structure of a typical pulse. And what about unstable double pulsing? Here are simulations of equal intensity double pulses with random relative phase. Notice that Frog sees the satellite pulse, but underestimates its intensity. However, discrepancies between the measured and retrieved traces indicate the instability, and the height discrepancy can easily be corrected just by looking at the trace, and this is also easily coded.
But the ultimate goal of pulse measurement is not only to measure stable pulse trains and to avoid being confused by unstable ones, it's also to definitively distinguish between stable and unstable pulse trains. Sure, discrepancies between measured and retrieved Frog traces indicate instability, but algorithm non-convergence, called stagnation, also causes similar discrepancies. And before Rana, previous Frog algorithms often failed to converge, even for stable pulse trains. And it's not even initially clear what convergence actually means when the always confusing coherent artifact distorts the measured trace, and it doesn't actually correspond to a single pulse. In which case, even in the absence of noise, there will be discrepancies between measured and retrieved traces, a quantity we call G'. Indeed, a large value of G' is in general due to noise, pulse shape instability, and possible algorithm stagnation. The good news is that it's easy to see and even mostly eliminate the effects of random noise in Frog. But as I mentioned, trace discrepancies due to stagnation are very difficult to distinguish from those due to pulse shape instability. So here we've plotted G' values for 100 runs for a simulated SHG Frog trace of an unstable pulse train, and with 4% additive trace noise. The most reliable standard GP algorithm available often yields large discrepancies, shown in red. In other words, its large trace discrepancies from many initial guesses are due to algorithm stagnation, not just pulse train instability. The Rana approach, on the other hand, always converges to the smallest achievable G' value, shown in blue, of about 0.2 in this case. Its G' error has no contribution from stagnation and is entirely due to the instability, and a little from noise. So Frog with Rana definitively establishes whether a pulse train has stable or unstable pulse shapes, and it solves this infamous decades-old problem. It also yields the correct pulse length, and for third-order Frog versions, the typical pulse structure.
Now, Frog has become the gold standard of pulse measurement. It and variations of it can measure pulses over a wide range of wavelengths, pulse lengths, and pulse complexities. It can even measure single-cycle pulses, attosecond pulses, and pulses on a single shot. Now, recall that I mentioned that a pulse measurement device should also be simple. Although Frog isn't really complex, it can be simplified. We can replace the beam splitter, beam steering optics, and variable delay stage with a single optic called a Fresnel biprism. And we can replace the thin nonlinear optical crystal and the spectrometer with a single thick nonlinear optical crystal. We call this simplified version of Frog grading eliminated no-nonsense observation of ultrafast incident laser light E-fields. Grenouille, the French word for Frog. How does Grenouille work? Grenouille's Fresnel biprism is simply a prism with an apex angle of about 170 degrees. It splits and crosses the beams in the nonlinear optical crystal. As a result, it maps delay onto transverse position at the crystal. At the top of the crystal, one pulse precedes the other, while at the bottom, the other precedes the one. Simply imaging the crystal onto a camera to the right maps delay onto position at the camera. This yields a single-shot measurement of a pulse. Even better, it stays aligned forever. To see how the thick crystal works, suppose that broadband light with a large convergence impinges on a second harmonic generation crystal. The green, blue, and purple ovals are polar plots of the generated second harmonic versus angle out of the crystal. Notice that the usual thin crystal yields very broad polar plots, indicative of its large phase-matching acceptance angle and bandwidth. The thin crystal is ideal for conventional autocorrelators, frogs, and most other purposes. Now, if the crystal thickness increases, each second harmonic wavelength's angular width decreases. There's no longer enough phase-matching bandwidth for most applications. And for an even thicker crystal, the curves narrow further. And an even thicker crystal yields even thinner curves. So a very thick crystal looks like a really bad idea, and it is for most applications. But if our goal is to spectrally resolve the second harmonic that's generated, then a very thick crystal is actually precisely what we want. And if our goal is a frog, notice that it not only yields the second harmonic as in an autocorrelator, but it also simultaneously spectrally resolves it, yielding a frog. So the thick crystal replaces the thin one and the spectrometer. For measuring about 100 femtosecond pulses, Granui uses crystals a few millimeters thick. So this is the Granui beam geometry as seen from the top and the side. It's a complete single-shot frog that uses the standard frog algorithm. It never misaligns, and it's more sensitive to the thick crystal. Non-linear optical processes scale as the square of the crystal thickness, and it's about 30 times thicker than a typical autocorrelator or frog crystal. And interestingly, it also measures the first-order spatiotemporal distortions of the pulse. We'll see how this works in a minute. In an extensive test of Granui, we found that it can measure most pulses very well. Here's a pulse with some structure, and measurements of it using Granui match frog measurements of it reasonably well, despite some laser drift during the measurements. Granui fails for extremely short pulses, less than about 15 femtoseconds, due to dispersion in the thick crystal, and it's hard to generate the required delays for pulses longer than about a picosecond. Otherwise, it works very well, and as an essentially single-beam device, it's very convenient. Now, ultra-short laser pulses can have spatiotemporal distortions. One such common distortion is shown here. It's called spatial dispersion or spatial chirp, in analogy with temporal chirp. What happens when such a pulse is measured by Granui? Well, the Fresnel biprism splits the beam in two and crosses the resulting pulse replicas, as we've seen. But now different frequencies overlap in different places in the second harmonic generation crystal. And we can see that the highest frequencies are generated at the top of the crystal and the lowest at the bottom. But these coordinates correspond to delays. So the otherwise symmetrical SHT frog trace will be tilted, and the trace tilt is proportional to the spatial chirp in the pulse. And as a result, the spatial chirp is measured. Another spatiotemporal distortion is pulse front tilt. And what happens when a tilted pulse is measured by Granui? As before, the biprism splits the beam into two replicas and crosses them. The green pulse has no tilt, but the red pulse does. The green pulse replicas cross in the center of the crystal as usual, but the red tilted pulse replicas cross off-center. The result is that the otherwise symmetrical SHG frog trace will be displaced, and the trace displacement is proportional to the tilt in the pulse, so the pulse front tilt is also measured. So how can we measure longer pulses from about 1 to say 30 picoseconds? Simple, use a Granui with a pentagonal second harmonic generation crystal, which combines the biprism and thick crystal into one optic. It crosses the beams inside the crystal, and it can measure pulses as long as about 30 picoseconds. And here are measurements of a train of about 3 pulses. It's a fairly complex pulse with a time bandwidth product of about 30, but the pentagonal crystal Granui can measure it quite well. What about even longer, say nanosecond pulses? Interestingly, measuring short, femtosecond pulses is easier than measuring longer ones. As we've seen, longer pulses require longer, often impractical delay ranges. To solve this problem in the 1980s, when many pulses were in this range, researchers introduced tilt into the pulse to be measured and built autocorrelators accordingly. In this way, they could cross 2 tilted pulse replicas to yield a much larger delay range in single-shot autocorrelators, and were able to measure pulses tens of picoseconds long on a single shot. But measuring a few nanosecond pulse would require one side of a 1 centimeter beam to precede the other, by a few meters. This corresponds to a pulse front tilt of 89.9 degrees. This seems quite impractical. Interestingly, it turns out that we can do this, and it's actually easy. The tilt introduced by an optic is proportional to the angular dispersion introduced by that optic. So prisms introduce some tilt, gratings introduce more, but an etalon introduces even more still. Indeed, 89.9 degrees is actually quite easy. So we still use a Fresnel biprism, but here just to split the beam into two replicas. Then a cylindrical lens focuses them to lines, one on the left side of an etalon, the other on the right. This introduces a tilt of 89.9 degrees in one replica and minus 89.9 degrees in the other. The two replicas then overlap in a second harmonic generation crystal, which yields the usual second harmonic light, which is then spectrally resolved using an etalon spectrometer not shown, and imaged onto a camera, yielding the usual SHG frog trace. But this trace has nanoseconds of delay range and high spectral resolution, and it's compact and naturally operates single shot. Here are nanosecond Granulli measurements of pulses from a microchip laser at 1064 nanometers. They agree with spectral measurements and also with our knowledge of the pulse spacing for the double pulse on the right. There's not great demand to measure such long pulses, but I just thought you might like to see how it can be done. At the other end of the temporal spectrum, near single-cycle pulses can be measured using some of the same ideas. First, as I mentioned, the thick crystal's dispersion makes it a bad idea for measuring very short pulses, so we'll need to go back to using a thin crystalline spectrometer. Also, as we've discussed, crossing beams at an angle yields a range of delays, and we don't need much of a delay range for this problem, so obviously we don't need to scan the delay. So all that's necessary is to cross beams at a thin crystal, image it onto an imaging spectrometer, and image its output onto a camera. But what's the best way to generate a small beam crossing angle without adding any extra dispersion? Well, not a Fresnel biprism, which has some dispersion. Instead, use a Fresnel bimirror. You can see it in the upper right of this slide. It's just a split mirror whose two components are slightly tilted relative to each other. Everything else is straightforward, and this turns out to work very well. I should also mention that people have used collinear beams and a scan delay, but this yields a very tricky algorithm problem, which is a work in progress. Here's another interesting pulse measurement problem, measuring two pulses at once. Chemists like to perform excite-probe measurements, in which they excite a medium with one pulse and probe it later with another. And often the other pulse is a different color. So they need to measure two pulses. Now they use beam geometry similar to those of frog, so why not turn their excite-probe beam geometry into a frog and use it to measure the pulses involved? Here's an example of a setup for a commonly used spectroscopic technique called polarization spectroscopy, which is basically polarization gating, which we talked about earlier. It involves a 45-degree polarized pulse gating a 0 or 90-degree polarized pulse, slightly rotating the polarization of the latter beam and causing some light to leak through the second of two crossed polarizers when the pulses overlap in time. But the geometry shown in this slide is a little different. It's sort of a double polarization gating setup in which one pulse polarization gates the other and the other polarization gates the one simultaneously. The word blind is used because it's related to a mathematical problem called blind deconvolution, and double because two pulses and two traces are measured. Here are measured and retrieved traces for two different pulses measured using double blind frog. Note the good agreement between the two sets of traces. And here are the two measured pulses along with the spectrometer measured spectra for comparison. Double blind frog works well for different color pulses also. Here are measured and retrieved traces for 800 and 400 nanometer pulses. Note the very good agreement between the traces. And here are the retrieved pulses and the spectrometer measured spectra for comparison. So double blind frog works well, and it's easy to adapt to most excite probe setups. Now, all measurements in science should have error bars, but in the days of autocorrelation, nothing was really actually being measured. The intensity couldn't be retrieved from the autocorrelation, and the autocorrelation didn't even attempt to measure the phase. One was simply measuring the autocorrelation for what it was worth. But now we're actually measuring physically meaningful quantities. So if we're serious, we should be able to attach error bars to a given measurement. Of course, figuring out the errors of a given measurement is usually quite difficult, and involves careful evaluation of every component in the device and every source of error. But for frog, it turns out that we can actually do this, and it's actually quite easy. Because a frog trace overdetermines the pulse, we can use what's called the bootstrap method. It simply involves randomly removing about half the points from a measured trace and retrieving the pulse, and then doing it again and again about 100 times, and then performing statistics on the retrieved points, then yields mean values and standard deviations for each point, error bars. Here are the intensity and phase of a simulated pulse whose frog trace was contaminated with additive noise. Note that the errors are about the same for all intensity points, as they should be. And also note that the errors in the phase are also until the points where the intensity is low, where the errors start to increase significantly. This is also as it should be, because when the intensity goes to zero, the phase becomes meaningless, so any measurement of it there is also meaningless. And here's a measured pulse with error bars. Note that the error in the phase near the intentionally introduced phase jump is large, as it should be. There are some ambiguities in frog. First is the absolute phase phi naught. This is because we measure intensity, not the field, so this is unavoidable. Next is the pulse arrival time phi 1, which is also unavoidable. All self-referenced methods have a gate pulse that's necessarily tied in time to the unknown pulse, not to our watches. Next is the direction of time, but only for SHG frog, and it's easily removed. Also, the relative phase of well-separated pulses in time, which varies from version to version of frog. And finally, the relative phase of well-separated modes in frequency, which are actually completely undetermined in all frog versions and all other known pulse measurement techniques. But most of these are generally considered trivial, meaning that they can be removed easily, though they're not important. Although the last one could be important in some cases. Now, the polarization direction of a pulse can take on any value in 2 dimensions, and this value can vary in time. Indeed, researchers often deliberately generate interesting shaped pulses whose polarization varies in time. How can such a pulse be measured? Well, most nonlinear optical processes require a polarized beam, so a measurement technique which uses a nonlinear optical process can only measure the intensity and phase versus time for one of the 2 polarization components. Of course, we can make 2 measurements, one of the pulse's vertical polarization and another of its horizontal component, by rotating a polarizer in the beam to 0 degrees, making a measurement, and then to 90 degrees, and then making an additional measurement. But in view of the ambiguities I just mentioned, we can see that this won't be enough. There'll be 2 ambiguities, the relative phase of the 2 polarization components and the relative delay between them. So we need to also find these 2 quantities. Fortunately, this turns out to be easy. In addition to making measurements with 0 and 90 degree polarizer orientations, just make another measurement using a 45 degree polarizer orientation in the beam. This additional measurement then yields these 2 parameters and the measurement is complete. This scheme works very well. It was invented by Randy Bartels and he calls it Turtle. By the way, here's a question for you to ponder. Can you have an unpolarized ultrashort pulse? So which method to use and when? Use Grenouille to measure pulses 15 femtoseconds to about a picosecond long directly from a laser. You can use it for oscillators and amplifiers. And we've already talked about how to measure longer pulses. For amplified pulses, you can use a third-order frog device to avoid the direction of time ambiguity. Now, amplified pulses usually have enough energy to make single-shot measurements in any device capable of doing so. If a pulse is complicated, and a previously measured stable reference pulse is available, use XFrog, provided that it's synchronized with and simpler than the unknown pulse. To simultaneously measure 2 unknown amplified pulses of any color at once, use double blind frog. If a stable reference pulse spectrum contains the unknown pulse spectrum, use spectral interferometry, which is what we'll be talking about next. But before we make this transition, I should mention that many methods have been proposed for measuring ultrashort laser pulses, and new ones are proposed every month. But many important features are necessary for a technique to actually be useful. Some techniques look great at first, but as we've seen, it can take years to find their flaws. For example, most newly proposed techniques are complicated. Some can only measure simple pulses, some measure only the coherent artifact, and others have algorithms that aren't reliable. Algorithm developers usually only report its operation for 1 or 2 pulses, they really need to test it on 10,000 or 20,000 pulses, and not just simple pulses. So it's definitely a buyer beware situation. I'm telling you only about methods that I know work well. Once we've measured a pulse, we can use it to help us measure another, perhaps more difficult pulse to measure. And a technique that does this is spectral interferometry. It simply involves measuring the spectrum of the sum of a known and unknown pulse, directly yielding the unknown pulse from the cross term in the formula for the spectrum of the sum of the two pulses. Now, before I say more, I should point out that spectral interferometry has the word interferometry in its title, so it measures only the coherent component of the pulse, and care must be taken using it. But because it uses a known reference pulse, as long as we know that that pulse is stable, and we should if we've measured it previously with a trusted method, then we can trust the result. Also, the fringe visibility can confirm whether a multi-shot measurement is of a stable train or not. So spectral interferometry is generally reliable, especially when it measures a pulse derived from the stable reference pulse. And when we use spectral interferometry in conjunction with frog to measure the reference pulse, we occasionally call it tadpole. Now, the good news is that spectral interferometry doesn't require a nonlinear optical medium, so it's much more sensitive than self-reference techniques like frog, which do. As a result, spectral interferometry can measure very, very weak pulses. For a 100 megahertz train of pulses, it has a sensitivity in the zeptojoule range. Indeed, we measured a pulse train with only 1/5 of a photon per pulse. On the other hand, spectral interferometry has a different issue. While it looks quite simple and easy to use, it's actually very difficult to use, to align, and to maintain aligned due to its use of collinear beams. In addition, the need to generate very fine spectral fringes requires 5 times the spectrometer resolution than would otherwise be required to measure the pulse spectrum. So we can use an easier to align cross-beam version of spectral interferometry, which uses spatial rather than spectral fringes, immediately gaining a factor of about 5 in spectral resolution over ordinary spectral interferometry. There are many versions of this approach pioneered by Silverberg and Squire and coworkers. Here I'll describe the C-tadpole version, which has some advantages as we'll see. It uses single-mode optical fibers to maintain alignment and beam quality, and at the camera, the non-collinear beams cross at an angle. Finally, dispersion in the fibers cancels out. Many measurements have been made using C-tadpole, and here's a pulse generated and measured by Matthew Coughlin and Robert Levis at Temple University. Using a pulse shaper, they generated a complex spectral phase, which C-tadpole measures, yielding an intuitive trace. And C-tadpole easily finds the pulse spectral phase. It yields the complex temporal intensity and phase shown here. And here's the C-tadpole measured spectrum, which is in nice agreement with the spectrometer measurement of it, but as you can see, the C-tadpole measured spectrum has better resolution than that of its own spectrometer. This is because it measures the spectral field, not the spectral intensity like spectrometers do, and it doesn't broaden as much as a result of the imperfect spectral resolution. C-tadpole can measure pulses with time bandwidth products as large as about 1,000. It's possible to measure even more complex pulses using a variation of C-tadpole that we call mud tadpole. It uses many reference pulses, each with a different delay. It can be done on a single or multi-shot basis. This schematic is of a single-shot version. Each reference pulse overlaps with a different temporal piece of the unknown pulse and generates spatial fringes with a different spacing. Keep in mind that the reference pulse expands by a large factor inside the spectrometer, in particular to the inverse of the spectrometer resolution, so typically about 50 picoseconds. And so each reference pulse measures about a 50 picosecond piece of the unknown pulse. The temporal range, and hence the maximum measurable time bandwidth product, is that of the C-tadpole device, here about 50 picoseconds, times the number of reference pulses. It's easy to generate a lot of reference pulses, and this increases the measurable pulse complexity by a large factor. This is a plot of the spectral intensity and phase of a very complex pulse with a time bandwidth product of 65,000, measured using a multi-shot mud tadpole device. It's so complex that this screen lacks the spatial resolution to plot it, so we had to make a movie of it. The wavelength is increasing with time during the movie. Now, I mentioned earlier that we really need to measure a pulse in time and space. It's not enough to make separate spatial and temporal measurements because EFT can vary from point to point in space. we need to measure the complete spatiotemporal intensity and phase, E of x, y, z, and t. Fortunately, sea tadpole has excellent built-in spatial resolution, which is determined by the spatial mode of the fiber, which can be very small. By scanning the input end of the unknown pulse fiber, it's easy to measure E of t at many different positions, yielding E of x, y, z, and t. Before I show you some complete spatiotemporal measurements, here's a theoretical plot of a perfectly focused pulse. We're looking at snapshots of it from the side as it propagates to the right. A perfectly focused pulse remains white versus x and t. Such a uniform color indicates a lack of phase distortions due to lens aberrations and other effects. This is a theoretical plot of a pulse focusing with spherical and chromatic aberrations as well as chirp using a singlet BK7 plano-convex lens. Color is instantaneous frequency. As you can see, theory predicts interesting and colorful distortions due to aberrations and dispersion in the lens. And sea tadpole confirms these simulations. Theory also predicts that overfilling a lens with an ultra-short pulse should yield complex structure at the focus, including a so-called forerunner pulse. And here we see that sea tadpole confirms this result as well. Another interesting optical situation is diffraction of a pulse due to a stop in the beam, which initially just creates a hole at the beam. The theory also predicts that the hole fills in from the center first, generating what's called a spot of Arago, in this case a pulse, in the center of the hole of the beam. By the way, in the next few plots, false color indicates intensity, not color. And here's a sea tadpole measurement of a pulse diffracting around a stop. Note the pulse of Arago is easy to see, and it's actually superluminal. It travels faster than the speed of light, and you can see it catching up to the rest of the pulse. Diffraction from an aperture is also interesting because the boundary is the same as for the stop. The so-called boundary waves are the same, so there's also a pulse of Arago. No one ever sees it, however, because the beam itself is so intense and spatially inseparable from it. But here we've temporally isolated it, so it's clearly visible. And again, sea tadpole confirms this effect. Finally, using a cone-shaped optic called an axicon, it's possible to generate a so-called Bessel beam, which is known not to evolve as it propagates. The same is thought to be true for Bessel pulses, so it's interesting to confirm this for a pulse. Here's a sea tadpole measurement of a Bessel pulse, which interestingly also propagates faster than the speed of light in vacuum, according to theorists, and confirmed by these measurements. It also retains its shape as predicted. The plots are for 3 times, and hence 3 distances. Okay, this is great and all, but making these spatiotemporal sea tadpole measurements required several minutes and a stable laser. But what if your laser isn't stable or has a rep rate of 1 per hour? Single-shot spatiotemporal measurement would be much better. So now, how can we accomplish this? Well, since there are more spatial dimensions than temporal ones, let's start with a technique that can measure the complete spatial intensity and phase of a monochromatic beam, digital holography. Digital holography works by measuring the intensity I of x and y of the sum of known and unknown monochromatic beams. The unknown monochromatic field, E of x and y, is then found from the cross term at the lower right. Now, to measure a pulse in both space and time, we need to realize that the unknown pulse spectrum is not monochromatic, it's actually broadband. This will require some additional innovations. First, we'll have to make many holograms, one for each frequency in the unknown pulse. And this will require a spatiotemporally known broadband reference pulse. So we'll need to pick off a piece of the unknown pulse and spatially filter it. We'll also have to measure it using frog, which will yield the required spatiotemporally known reference pulse. So we've developed a technique that we call striped fish, which accomplishes this and is also quite simple. Striped fish makes many simultaneous holograms, each in a different color. It requires only 2 optical components, a coarse grating to yield multiple pairs of beams, and a bandpass filter whose central bandpass wavelength naturally varies with incidence angle. Each hologram provides the spatial intensity and phase for that color. The frog measurement of the reference pulse also yields the relative phases of them, completing the measurement. Striped fish yields the intensity and phase versus space for all frequencies in the pulse, E of x, y, and omega. Then a diffraction integral yields the z-dependence, and finally, inverse Fourier transforming this result yields E of x, y, z, and t. So striped fish yields the complete spatiotemporal intensity and phase in all 4 dimensions on a single shot. This is a theoretical schematic of a striped fish trace of a simple pulse. Due to the bandpass filter, wavelength varies across the screen from left to right. Notice that the array of holograms is tilted. This is because the coarse grading is intentionally tilted, so each hologram occurs at a different angle and hence at a different color. This is a typical measured striped fish trace. There are about 50 holograms, and each is about a 100 by 100 array. These numbers can be easily varied according to whether the pulse is more complex in time or space. And this is a pulse completely measured using striped fish. It's coming out of the screen at us, and color indicates instantaneous frequency. It has several spatiotemporal distortions: temporal chirp, spatial chirp, and pulse front tilt, which you can see from the movie. Here's a striped fish measurement of pulses emerging from multispatial mode fiber. At a wavelength of 800 nanometers, this fiber has 4 modes, which have different group velocities. For striped fish measurements, we're using a different method of plotting color, using RGB integrals, so the pulse looks as it would to the human eye if the eye had about 12 orders of magnitude faster temporal resolution. The different modes emerge from the meter-long fiber at different times, but they have similar dispersions, all appearing white. Rotation of the mode pattern is due to the superposition of degenerate modes. Speaking of spatiotemporal distortions, there's an interesting one called the ultrafast lighthouse effect. It involves the beam direction varying in time, just like the beam emitted by a lighthouse. Looking down onto the lighthouse beam, you can see that it's a spiral in space and time. It turns out that this effect also naturally occurs to ultrashort laser pulses, although not quite by such a large amount, just a few degrees. Nevertheless, it has interesting applications, such as selecting out a single pulse from a train of extremely short attosecond pulses, which are otherwise separated by only a few femtoseconds, as proposed by Fabien Carré. But it's important to confirm that such an effect really does exist. So here's a striped fish measurement of an ultrafast lighthouse. This slide shows different ways to plot such complex 4-dimensional results. But however you plot it, you can see that this pulse's propagation direction is changing with time as it propagates.
And recently, my grad student Liz Grace used striped fish to measure individual terawatt pulses of the 1 shot every 5 minutes comet laser at Lawrence Livermore National Lab in California prior to its refurbishment. Also, her measurements revealed for the first time shot-to-shot variations in the fine details of such pulses.
Okay, at the beginning of this talk, I said that improvements in light measurement techniques have led to great scientific discoveries and technologies. So what kind of applications might there be for pulse measurement techniques? Well, for millennia, mariners have returned from sea voyages with incredible stories of gigantic ocean waves in otherwise good weather. Waves whose heights were so extreme that Gaussian statistics implied that they could only occur once every 10,000 years. So these mariners weren't taken very seriously by scientists. But pictures and videos have now conclusively proven these waves' existence. Indeed, dozens of ships sink every year with no other explanation. It turns out that the physics of ocean waves is highly nonlinear, so Gaussian statistics doesn't actually apply, and rogue waves are now known to be much more common than ever imagined. Since lives are at stake, it's important to better understand this dangerous phenomenon, and a better understanding of rogue waves could help predict them and perhaps even allow ships to avoid them. But because they're still relatively rare and appear to occur randomly, they're difficult to study. And even if you could make one, maybe you shouldn't. Interestingly, Jalali and coworkers recently showed that the physics of oceanic rogue waves is similar to that of optical rogue waves, which occur in supercontinuum generation in optical fibers. While it's very easy to measure an oceanic rogue wave, they're hard to miss. Measurement of an optical rogue wave isn't so easy. Supercontinuum is the most complex ultrashort pulse ever generated. It has to be if it's going to mimic the ultra-complex ocean surface in the presence of oceanic rogue waves. A clue as to how to do this comes from the fact that optical rogue waves are best identified in spectrograms. Numerical simulations of supercontinuum yield spectrograms where optical rogue waves are easily seen. So how can we measure a spectrogram of an optical rogue wave pulse? Let me think. Wait, frog directly yields a spectrogram. Nevertheless, measuring such a complex light pulse is not trivial. The spectrum can be hundreds of nanometers wide, and nonlinear optical crystals just don't have those kinds of bandwidths. To reduce the required nonlinear optical bandwidth somewhat, we can use a narrower band reference pulse to gate the continuum, not the continuum pulse itself. In general, it's better to gate an unknown complicated pulse with a simple known one. This yields an X-frog measurement, but that only buys about a factor of 2 in bandwidth reduction. The more important trick is to angle dither the crystal and integrate over time, which drastically increases the crystal bandwidth. The delay must also be scanned, so this is inherently a multi-shot technique, and indeed quite a few shots will be required. And here's the resulting X-frog measurement of continuum. Although the measured and retrieved traces appear to agree on a large scale, notice that there are big discrepancies in the details. There's a polka dot pattern in the retrieved trace, which is not present in the measured trace. In addition, the spectrum retrieved from the X-frog trace is very complicated, while the spectrum measured using a simple spectrometer is much less so. So which is correct? Of course, you all know what's happening here. Such discrepancies between the measured and retrieved traces can only mean that the supercontinuum pulse train is highly unstable. We can check this by measuring actual single-shot spectra using a simple spectrometer, which nicely reveal the instability and the fine structure in each individual pulse spectrum. In black is the average of 4 measurements, which shows how quickly the structure averages out in spectrometer-measured spectra. What's remarkable is that despite the supercontinuum frog measurement averaging over literally 100 billion pulses, it not only reveals the supercontinuum instability, but also retrieves an accurate typical supercontinuum spectrum. Pulse structure just doesn't wash out in frog measurements. Now that's great, but to actually study optical road waves, we'll need a true single-shot technique capable of measuring the extremely complex supercontinuum pulse. It turns out that we can actually do this. First, we need a huge nonlinear optical phase matching bandwidth on each shot. To accomplish this, we use the third-order nonlinear optical process, polarization gating, which inherently has essentially infinite bandwidth. And of course, we also need to use a single-shot beam geometry, so we'll have to map delay onto transverse position at the nonlinear optical medium. Now, because they're so complex, supercontinuum pulses are also relatively long, so we'll need to use a tilted reference pulse for more delay. Unfortunately, a new complication arises, however. In polarization gating, the delay varies along the beam. This so-called longitudinal delay smearing reduces the delay resolution, which is bad. But the good news is that using a tilted pulse can actually cancel out the delay smearing, so the device works. So here's a true single-shot measurement of supercontinuum from a photonic crystal fiber. The time bandwidth product is 65. There's also good agreement with a spectrometer measurement of the spectrum, although the spectrometer spectrum was contaminated by fiber cladding light. And here's another single-shot measurement of supercontinuum from a photonic crystal fiber. Here, the time bandwidth product is 96. And finally, here's another single-shot measurement of supercontinuum, this time from single-mode fiber. This technique can also measure even more complex pulses, but we ran out of money before we could push the technique to its limit. So the challenge of developing ultra-short pulse measurement techniques hasn't been quite as easy as everyone first thought, or even still thinks, and misinterpretations and mismeasurements remain common. But at the same time, there's been tremendous progress. The techniques that work are quite powerful and also quite easy to construct and use. And we can now easily and reliably measure essentially every aspect of almost every pulse ever generated, and many that have not. And there's no reason not to take advantage of these methods. But now if I hear that you're still measuring only autocorrelations or coherent artifacts, know that you'll be setting science back 3 decades, and words won't be able to describe how disappointed your parents and I will be in you. Instead, it's now time to use these more powerful light measurement techniques to measure interesting and important light pulses and maybe discover something that'll change the world. Thank you very much.